We expect devices to handle a massive range of information. You read foreign alphabets, hear crystal-clear symphonies, and watch photorealistic sunsets. But the silicon processor inside your device does not perceive the shape of a letter, the pitch of a violin, or the warmth of sunlight. At its core, it only recognizes two states, on and off, ones and zeros. This creates a mechanical translation problem. The real world is analog, a smooth, continuous stream. To put reality inside a computer, we must divide it into discrete digital boxes called bits. Restricting reality to a small number of these boxes creates a bottleneck. Details are lost in the transition, appearing as jagged pixels, or robotic audio, or text systems missing specific characters. The quality of our digital experience depends on the specific volume of binary data we assign to represent it. Early computing prioritized efficiency due to extreme memory constraints. Engineers represented text using a system called ASCII, which relied on just 7, and later 8, bits of data for every character. 8 bits of binary data allow for exactly 256 different combinations. This chart shows the limit. 256 slots provided enough space for the standard characters found on a mid-century American keyboard, but nothing more. This mathematical cap excluded languages with thousands of unique characters, like Chinese and Japanese. Without available slots in the grid, the machine could not process their written form. Unicode addressed this by expanding the data capacity per character to 32 bits. This provided over 4 billion potential combinations. This expansion enabled computers to process Arabic script, kanji, and Cyrillic alongside the Latin alphabet, making the technology globally accessible. Sound faces a similar constraint. Physical audio travels as continuous waves of varying air pressure. To digitize a voice, a microphone measures the amplitude of that wave thousands of times every second, a process known as the sampling rate. Accuracy also depends on sampling resolution, the number of bits used to record the loudness of each snapshot. An 8-bit resolution offers 256 possible values. These large digital steps fail to track the wave's curve, resulting in robotic audio. Increasing capacity to 16 bits provides over 65,000 distinct values. The steps become finer, allowing the digital signal to trace the contours of the original wave. Allocating more data allows the binary simulation to recreate the nuance of natural acoustics. Visual media follows the same logic. Computers interpret images as a matrix of individual squares, or pixels. The density of this grid is the image resolution. A 1-bit pixel has only 2 options, 0 for black or 1 for white. At this depth, an image is reduced to a jagged 2-tone silhouette. Capturing gradients requires expanding the color depth, the data assigned to every pixel. Today, a 32-bit color depth is standard. With 32 bits, a single pixel can represent one of millions of specific shades. It blends red, green, and blue values with high precision. Deep color depth hides the underlying digital grid behind a massive volume of binary data, creating the illusion of a smooth photograph. Text, sound, and imagery are distinct to human senses, but a silicon chip processes them using the same fundamental mechanics of bit allocation. A larger file size reflects a more granular representation of the physical world. Preserving global cultures through Unicode, capturing vocal clarity through sample resolution, rendering cinematic gradients through color depth, all require the same thing: more data. Computing has moved away from the restrictive 1-bit and 8-bit bottlenecks of the past toward the 16-bit and 32-bit densities we use today. Every additional bit of data narrows the gap between a digital simulation and the continuous reality it represents.